Okay. Okay, so I'm Varvara Murphy. I'm a Senior Partner Solutions Architect, and we're really excited to bring you Achieving Scale with Amazon Aurora Postgres Limitless database.
I'm Venkatesh Periyathambi, and I go by Venki. I'm a Principal Data Architect, primarily focused on open source engines, so happy to be here. So Varvara will lead the session the first, and I will join her later on in the session. Right, yeah.
Okay, just quickly on the agenda. So we're going to look at scaling challenges, and then we're going to introduce Limitless and its architecture, talk about data distribution, transactions and queries, and then we're going to do a few Aurora use cases. Okay, so scaling database, and this is just a very simple slide, but over time, databases scale both on their data and their requirements for transactions. So as the IOPS increase, there comes a stage when you can only size up your database to a certain amount, and you reach the capacity limit for a single database. So this is where sharding comes into place to bring scale by parallelizing your queries. So this is just an example of an application where we've sharded around a character A to F, etc. So that might be your customers or whatever. So you're parallelizing your queries. You're going across multiple instances, not just one instance, and that way you're achieving scale. So we have people that have done this. We have customers that have implemented this on various platforms, and there are some problems associated with that, the challenges that that brings. So the first is around querying. How do you distribute your queries across those shards? So you're trying to get access to your data across the different shards. How do you route the queries to the correct one? Consistency. How do you contain consistency across commits, say, across your database? So, for example, you're dealing with different joins and you're doing effective query parsing. And then you're looking at consistency. So consistency on your application to ensure that you have a transactional consistency. So different parts of your query are going to do joins across different shards. And then you've got maybe your schema consistency. As you add new columns or you change your schema, how are you going to maintain that across the different shards as well? And then challenges around maintenance. So, for example, this is just showing you an example of a backup. You want to maintain a consistent backup. You've got multiple database instances. So finally, then resharding. So when you get a hot key, how do you reshard that database effectively to minimize your application so that you want it to be efficient, and how would you handle that in a multi-database system? Capacity management, and again, when we're looking at the cloud, this is really important. We don't want to over-provision, under-provision, so we've lots of instances now, so the costs are going to be multiplied. So capacity planning is also really important. So with this in mind, at reInvent, we launched the Aurora Limitless database on the Postgres compatible version of Aurora. So this gives you the power of a sharded database with the simplicity of a single database, so your management simplicity of a single database. And it provides extreme scalability in a managed service. So you can scale now to millions of transactions per second and petabytes of data. And all of this is going to give you transactional consistency within the entire system. So it's using a distributed architecture to scale. So it's under the hood, it's using all of our technology from the Aurora systems. And in this case, you get a lot of the features of Aurora. So you get the durability of the storage, high availability, and you get your deployment. You've got your monitoring tools like CloudWatch and Performance Insights, and you've got a pay-as-you-go pricing. So how do you provision this? So if you're looking at provisioning it up, so you could use the APIs, but if you just go into the console, you'll see there's an extra drop-down for Limitless, for the version for Postgres. Currently, it supports 16.6, and now we've got another concept of a DB shard group. So the DB shard group uses Aurora serverless under the hood, so the same technology. And if you've used Aurora serverless, you'll be aware of the concept of Aurora capacity units. So an Aurora capacity unit is 2 gigabytes of RAM and the associated compute and networking. So within this shard group, which is where all the resources are allocated, you can scale between a min and a max of those compute resources, of the ACUs, with a minimum of 16 ACUs and a maximum of 6144 ACUs. So that will give you over 12 terabytes of RAM effectively. So instead of a fixed capacity, you're scaling between this capacity range, and the database shard group scales within that range. And again, it's supported by the 99.99% SLA, availability SLA, as per Aurora. There's also the concept of redundancy. You can have no redundancy, 0. And again, you provision, this is at provision time, or you can have a redundancy of 1 or 2, so that's across the availability zones for those resources. So looking at the architecture, we're going to look at this in terms of an e-business application, or an e-commerce application. So we have our tables, our customers, our orders, and our tax rate table. And we're going to just look at it in terms of this. So this is just a simple sample schema. So you're going to notice between the customers and orders, which are huge tables, they have a common customer ID key. So a lot of the joins will be across the customer IDs. The tax rate table is a simple lookup table. It might be small. There might be a little DML on it. So, and that's going to be used as well in all the joins. So if we're looking at the Limitless database, in terms of the tables, we've got the standard Postgres tables, but we've now got 2 extra tables. We've got our sharded tables and our reference tables. So for sharded tables, the tables are going to be sharded, so they're going to be split across all your instances shards based on a shard key. So if we look at orders, and I've color-coded it here for customer ID, so each of the customer IDs have a different color. And if we've sharded on orders, on customer ID, that places the customer IDs with the same, the tables, the rows with the same customer ID on the same shards. Now, I mentioned before, customer and orders are often joined together. And so we want to co-locate the table customers with order. So they're co-located on the same shards. And again, split by customer ID. They're sharded based on the customer ID for the customers table. So you can see where if you'd have in a single shard query, you'd have unlimited scaling for those queries. So the reference tables for tax rate, so this is a small lookup table like I mentioned, and again, it doesn't have a customer ID, so it doesn't lend to sharding, but it is used in a lot of the joins, and so therefore the full copy of the tax rate table is allocated across all the shards. Okay, so just stepping back a bit to look at the Aurora architecture. And we're going to look at this in sort of comparing it to a standard Aurora architecture. So we're just looking at the standard cluster now. We've got the Aurora distributed storage. This is going to be our foundational Aurora distributed storage where our data is stored, and it's a distributed shared cluster volume. It's highly durable, and it's replicated across all of the availability zones. And it also has lots of the features for performance enhancements built into Postgres. On top of our storage, which is holding all our data and can scale independently, so it's basically what you have is the ability to scale your storage and your compute independently. So they're independent of your storage and compute. So you're going to have your applications are going to connect into your instances here. In this case, you always have a writer instance, and you optionally have up to 15 read replicas. So these read replicas could either be used for failover, so for high availability, or they could be direct your reads across those reader instances. So your application read traffic could be directed across those. But in any case, you can see that the writer instance is where your writer capacity is going to be capped. So you're going to have a capping based on the size of your writer instance. So on Limitless, We still have the Aurora distributed storage, but we have this concept of a limitless database shard group. So the storage is unchanged, but what we have is that we've added this shard group, which writes as well as reads and handles your application traffic. So with this Limitless, we have replaced all the writer and reader instances with this shard group, and that contains the compute that's going to power your Limitless database. So no longer have you got your capacity capped on your writers now. So the application points to this one endpoint, the Limitless shard group. So looking inside the shard group, it's contained within the Aurora cluster. So all your maintenance commands will happen across all the shards. So it's operations like backup and upgrades are automatically applied to the shard group, so you don't have to manage independently. And it encapsulates all of the infrastructure powering your Limitless cluster. So within that, we've got the data access shards and the distributed routers. And instead of reader and writer endpoints, the shard group provides this new endpoint for application connectivity. It scales resources within the configuration, so it scales vertically and horizontally based on load and data size. And now we break that down into looking at the distributed transaction routers. So these serve all your application traffic. So the shared group endpoint resolves to the routers, and they themselves, of course, can scale vertically in place based on the load. And the database control plane can also add more routers into your shard group if they reach the vertical scaling limits. So routers store metadata and not data, and they know the schema and the mappings for your key ranges and shards. So they're not simple proxies, they're coordinated time-based transaction systems. And so they're responsible for assigning the time that your transaction gets when they're performing when they reach your router. And so if you think of it, so that would give them the read and isolation consistency required, the transactional isolation consistency required for your transactions. In this case, so for commits across a multi-shard write, they will handle the distributed commits, and they are also they perform they're actually a full implementation of the Postgres. They're an engine, they're a database engine, so they perform the initial planning of the query and they aggregate the results from a multi-shard query as well. So now we look at the data access shards. So the data access shards, they own a portion of the sharded key space, the sharded tables key space, and they've got a full copy of the reference tables. So like the routers, they can scale vertically in place based on, and as the load gets bigger, they can actually, if it gets too high or the amount of data stored is too big, they'll actually split the shard, creating a new shard. And they're using the Aurora storage mechanisms to clone the key ranges under the hood, and Venki will talk about that later on. So the shards receive a transaction context and a plan fragment from the router. And they're responsible for their own plan then, so they create a sub-plan for the shard, whether it's going to do a full table scan or an index lookup, and they will execute that, and they will drive local commits. So that they are all, and they're also backed by the Aurora distributed storage. So just looking at topology and availability, again, if you're looking at it from a traditional Aurora cluster, when you provision up a cluster, you're getting your subnets and you're allocating your instances across availability zones. So your writer instance in one availability zone and maybe multiple readers for failover. So in terms of Limitless, we have designed this as a regional implementation. So all of the cluster's shard group components are allocated across all of the availability zones. So it's regional in implementation. So in this case, we've got an example of a redundancy of 2. And you can see that the router has got, so the shard groups have all copies of the shard. So if we lose any availability, so one of the other database access shards can take over. The distributed transaction routers only hold metadata, so they're, and I have to say this word, fungible. Whoever found that they definitely use Nova for that one. But so it's fungible, so they can be replaced as necessary. And so that's just a quick overview on the topology. I'm going to hand it over to Venki for the second part of the presentation.
All right, thank you, Varvara. So I will start with the data distribution, and before I go further, I will show you a quick example of how to create these tables, right? So what you see on the screen is how you're going to create with the create table mode and create table shard key. And these are session level variables. So right after you set this and you create a customer table with the customer ID as your key, this is going to get sharded automatically into the number of shards you define at the ACUs, right? And for co-located, here is the syntax. Just like a regular table you're going to create here. When I say regular, Limitless only has sharded. It's not your standard table. You can convert your standard tables to sharded using the command that I shown earlier. But for co-location, you're going to give a syntax to show which table you're going to co-locate with. So you had the customer table earlier. You're going to co-locate this outer table with the customer table, and that query will take care of that. And then for reference, it's pretty straightforward. You're going to put this table mode as reference. And that way, the tax rate is going to be in all the shards. So this is, so let's say you start writing the data into it. So each shards will have the actual copy of your reference table, unlike the sharded table, which only have the key ranges. I will go more into that. But if you want to learn more about how these tables are laid out internally into the database, do a regular describe table of your Postgres, and what you see on the screen at the bottom is these tables are partitioned. So the customer table which we created earlier, and you would see 4 partitions here, and obviously as your data grows, this will grow, but this is just an example. But the interesting part here is the hash key on the customer ID table. So what we do here is we take this hash key, which is a 64-bit space. Then you have this multiple range now. We're going to take or split this into multiple ranges. We're going to assign this range to your sharding. So if you have 100 shards, we'll make sure these ranges are allocated properly, right? And this is just an example of 4. And double clicking on hash range partitioning, I already spoke about the 64-bit space and how those ranges of 64-bit space are being allocated to the shards. One thing you have to understand is these shards don't have your full table. They only own fragments of your table. So in this case, if you have million rows, then each shard probably will have pieces of your million rows. Then the routers are intelligent enough, like Varvara said, right? They hold the metadata of these hash key, what you call. So when a query comes and connects the router, it exactly knows where to send the queries to. So in this case, if you are trying to reach shard 3, it's gonna it has the metadata already, which range it's going to send it through, and it will plan and it will send it to the corresponding shard. So for scaling out, this is an important piece here, because you might wonder, when you create this cluster, probably you had million rows over the time, 10 million, 100 million rows, and your data is exponentially growing. And probably one of your shard is getting busier. It could be due to workload, your IOPS consumption, or perhaps it's too much or too many rows are being inserted into that particular shard. And that's when we're going to introduce the shard split. So take this diagram, for example, the very last shard that you see. We will do the shard splitting, what we call, and I'm going to talk about how we handle the shard splitting so that you don't really experience any interruption while we do it at the back end, right? So in order to do that, we leverage Aurora Clone and Aurora Global Database Replication. So these are 2 different technologies which we've been using in Aurora. So we're going to leverage that in order to bring this capability. For those who aren't familiar with the cloning, I will give you a quick rundown. Aurora cloning, basically what we do is you have your storage, we create a clone of the storage, but we don't provision any data in it. But rather we do a reference to your original storage where you took the clone from. And as and when you make changes, we use copy and write protocol to push the changes to have the data into the clone. And with respect to global replication, so that's a piece we use with Aurora Global Database. So imagine you have 2 different regions. So 2 regions will have its own storage. So anything you write in primary region 1 will go into primary region 2. And the way we do is we don't do a logical replication. We rather do a storage level replication on a log based, not a file based. So we combine these 2 technologies in order to make this shard split to happen. So let's say you have this shard which I showed earlier. We're going to do a clone. Then we're going to do a global replication so that now you have 2 shards with the same data, right? Then we start trimming down the hash keys. So perhaps the 4th one will have the first half of your key range. The last one will have the later half of the key range. And we trim it down, and then the routers will automatically reference the new shards which got created under the hood. This is all done automatically. You don't need to manage any of these. It's all handled for you. So you continue to write when this whole operation happens behind the scenes. And as far as routers are concerned, it can scale in place or it can scale horizontally. So you can add these shards automatically based on the workload. And again, that's something we do it for you. You don't need to worry about that. So that's the animation part. So here's the reference table. To again reiterate Varvara's point, the main intention of having these reference table copies in each shards is to avoid the network latency, right? Imagine if you have this reference table in just one shard or pieces of it across all the shards. And if you have to do a join, you would probably have to access multiple shards to do it. But if you have a full copy in each shards, you are going to avoid this hop between these shards, right? So that's why we are having this full copy. And the entire intention is not to scale the writes for the reference tables, although it can handle writes. It's more read focused. But it can handle writes, and it is strongly consistent. So meaning you have, let's assume you have 10 shards, you have this reference table in 10 shards. And suddenly you decided to change the schema, right? It is strongly consistent, meaning we don't write in one node and then later replicate asynchronously. We rather write it simultaneously across all the shards, then we wait for it to commit before showing the data to you. So that's that. Moving on to transactions. You might wonder, yes, we did say it's a Postgres system. What you have done is we have taken the whole Postgres community protocols. We started tweaking a little bit, but we kept the semantics as you would normally handle a Postgres instance, right? You get this read committed and repeatable read. So these are the 2 isolation levels available today in Aurora Limitless database. So as a user, you get to enjoy the Postgres semantics just like how you would enjoy in a single node system, except you have multiple nodes running behind the scenes, but you don't get to feel that you're working with multiple nodes. And that's the design goal, but it's not easy to implement because we have some challenges. I'm going to quickly run down through the challenges. If you have a single node, it's easy to track. So Postgres, what does it do? It tracks all the running transactions, it coordinates, but the downside is you won't be able to scale. And in order to scale, you will probably have to add more nodes, but in order to keep the scalability and performance together, you would have to reduce or eliminate the coordination points. Then you may have transaction which could be small or long running transactions, implicit, explicit, and you wouldn't know when this transaction is going to commit in a distributed system. In a single system, you exactly know, but in distributed system, it's a different story altogether. And then you may have queries. Let's say a router receives a query, it may send it to different shards at different times. It may commit at different times as well, and it may try to read the data while it's writing. So there's a lot of moving pieces there, and that's something you have to maintain. And the order of events is something you have to maintain in a distributed system, because if you keep writing and reading another transaction, you have to have a consistent view. That's only possible if you maintain the order of events in a transaction, and you have to do this in a distributed system. So these are some of the challenges, and most importantly, you have this backups, restores. Just like how you get that consistent view on a single node system, you would have to have the same consistency, except this time you have a distributed system. You don't want to have missing transactions or one-off writes or so on, right? So these are some of the challenges we had to fix. I will show you how we fixed, but before that I will show you what sort of properties you get with the Aurora Limitless, right? So when it comes to the ACID properties, like I said, you get repeatable read and read committed. And in order to maintain the order of events, we have something called external consistency. And this is something you don't see in many distributed databases, but Aurora Limitless does. What we do is, let's say you have an active transaction running and it's about to commit. Any active transactions that are coming afterwards, you would have to maintain the order. You would have to wait for this transaction to complete before you process the other ones that has come afterwards. And this is to preserve the order of events. So for example, you have a bank account, you want to put money in and out throughout the day, and at the end of the day, if you check your bank, you would have to see probably your balance. And if the orders are mixed up, probably you won't get an ACID consistent view. And while preserving this order, you get to have a consistent view, and we managed to achieve this using this external consistency. And multi-shard writes are atomic, so you can write in single shard, multi-shards, it doesn't matter, you still get this atomic writes across the nodes. And DDLs are transactional and strongly consistent, just like Postgres and multi-shard system. And you don't need a special connection drivers or something. You can use the endpoints to make this happen. And you get the consistent snapshot and backup and point in time restore. So we spoke about it, so I'm going to skip that part. So how did we solve this, right? So we use something called EC2 time sync. So we took this Postgres protocol. So before we send these transactions down, we tweaked this protocol to add this timestamp, and that's very crucial. And timestamps are important, right? I will tell you why in a minute. But it leverages EC2 time sync service to do it. It is a satellite-based atomic clock with microsecond precision. I'm referring to microseconds, right? And we have that microsecond precision for a reason. I'll give you an example, right? Imagine you want to send some invites to your friends. So you go to a postal office, you're going to post letters. Imagine you have two friends, you're sending 2 letters. And the post office guarantees you like 2 days. In 2 days, you're going to get it. One user may get it a day before because probably it uses a different route. The second user probably get it after 2 days. Again, for various reasons. You can't question why. But to ensure that both the receivers have received your letters, you could probably wait 2 more days or 3 more days. So you know for a fact they would have received it regardless of whatever delays they've gone through. This is exactly the concept we have done with this timestamp. So we have this earliest possible time. So that's the time where you think it could have received. And then the latest possible time is the buffer period that you're going to wait to ensure that they have actually received, or they should have received. So that's the sort of time that you're going to leave it there. And with these 2 times, we have done some rework on how the commits are done to make sure your transactions are consistent across the system. Why did we do that, right? Because you may keep writing, and then another part of the side, you may try to read the same transaction. You get to have this consistent view. And we managed to do it with this timestamp service. Be it a single phase commit. If you're writing on a single shard, it's going to use a single phase commit. If you're touching multiple shards, it's going to use a two-phase commit. And while doing this, we're going to play with these timestamps to ensure while it's getting committed, it's going to refer these two timestamps to do it. So I have an example in the next slide. So it is a time-based MVCC rather than transaction-based like Postgres. But before I show you an example, I'm going to quickly show you the query flow of how a query flows with Aurora Limitless. The router is going to receive a query from your client. It's going to make a plan to see which nodes it has to send the queries to, and what are the joins that it has to do. So it's going to send the queries to the shards with the transaction context, and while doing so, it will attach this timestamp. And shard, when they receive it, it's going to receive the partial query. It plans this local joins and scans. It's going to execute and send the results. Again, shard is capable of using this timestamps. You will see that in a minute. Then once the results are sent back to the router, the very last step is when the router does the final joins, filters and aggregations as necessary. So this is the example here. Imagine you have a transaction T1, we're going to open with an isolation level. I'm going to run a query on customer ID 619. Imagine this is a separate shard because customer ID was a shard, right? So 619 is a shard, and the timestamp which I mentioned earlier, right? So router is going to get a time of T100, just to make it simple. I don't want to go with microsecond timings here. And with that time, it's going to execute the query on the shard 619. You get the result, which is filling, just a state of your order. While this transaction is open, you're going to run a parallel transaction T2. You're going to run a query, but this time you're going to touch a different shard key, which is 801. It's a different shard altogether to check the status. So because this query is run at a later time, 103, let's just say we ran it later, 103, it's going to execute the query at 103 on the shard 801. It gives you filling. It's a coincidence. Okay, great. So now I'm going to flip this update. I'm going to run this update query to change the status to shipped on this 801 on transaction 2. And if you notice, I have touched only one query, only one node, which is 801. So it's going to be a single shard activity. I'm going to use one phase protocol. So how do we do it, right? So the router decides to use one phase commit on shard. Then shard assigns a commit at T10. So if you notice, the router gets 103, but the shard gives a state commit time for T10, which is what I said, right? And you want to wait for the 2 extra days. So that's 210. That's a late possible time. And it's going to commit, and it's going to give you an acknowledgement based on 2 conditions. 1, the writes are durable on disk. And 2, the earliest possible time should be greater than T10. So which is T110 or 110. And it has to, these 2 rules have to be met in order for the commits to go through. So now let's say it's done. I'm going to open a T3 transaction. I want to check the update which I've just performed on shard 801, or so customer ID 801 on the shard. Same thing, later time, I get a time 125, I'm going to execute, I get the status shipped because it has gone through, so anything that I read after the write, I get the data that I just updated. But the T1 is still open. Let's have some fun. Let's go there and find the status of 801, because imagine the T1 was kept open throughout this T1 and T3, but we haven't committed it, so it's still open. So while that's open, the time is T100, which is way before you've done these updates. So what do you expect to see? Do you expect to see filling, or do you expect to see shipped? Because it's a repeatable read, you expect to see the change or before the change was done. So it's still going to use a T100 snapshot, and it's going to give you the old status, which is filling, not shipped. That's repeatable read. Traditional Postgres, in an open transaction, you don't want to see dirty reads, right? So that's the whole point, and this is how we maintain the semantics of Postgres in a distributed system. And I had another diagram which I didn't want to show because it will make it boring. That's a 2-phase commit, but you get the idea of how we play with the time. So the timings that you see here are 110, 103 or whatever, right? But in reality, we are looking into a microsecond. So there is no additional latency that you experience in real time. These are negligible in real time. So here, we'll make it interesting. Last few minutes of the slides. So I'm going to make it more interactive to see which use case we have to use or which services we have to pick for these use cases, right? So here is a fictional use case we have created. Have a read, but it's pretty straightforward, right? If you notice the ones in yellow, you as a company, you're having thousands of transactions, and I need real-time reporting without disrupting the primary with a predictable workload, and I need high-performance database. So, Varvara, which database should we pick? Should we pick?
I would reckon Aurora Provisions, and the reason we'd do that is because we know the capacity, we know where the peaks and troughs are, whereas we could choose Aurora serverless if there was an unknown peaks and troughs, so if you didn't know what capacity you might be using.
Yeah. That's right. So this is Aurora provisioned. That's a use case. You might wonder why we didn't go for serverless. Because we know that you're going with the steady traffic, we picked provision. So if, let's say, you have an unpredictable workload, simply you could switch to serverless with a click of a button. And that would still be right because everything else that's in the requirement would still fit for serverless. It's just the predictability plays a factor here. Right, so the next use case, again a quick one. You have millions of transactions holding several terabytes and still growing day by day, right, going through the roof and in dire need of sharding, which is also looking for data resilience. And if you look through this use case, again, which Aurora flavor would you pick for this use case? Would I pick provision here?
Well, obviously, this is a really good case for Aurora Limitless. You've got sharded technologies. You might have larger than the 128 terabytes for your storage, and this is a really good use case for Limitless.
Yeah. So if you wonder why we didn't pick provisioned or serverless, because we are going beyond 128 terabytes. That's your traditional Aurora limits, right? But with Aurora Limitless, you could go beyond your traditional 128 terabytes, and you could probably do provisioning, but you have to maintain the sharding yourself. But you are looking for a managed sharding service, and Limitless does that for you. It's a managed sharding service beyond 128 terabytes, so that's the use case for this. And the last one, before we wrap it up, another use case, it's very tricky. You need an active multi-region where customers try to book tickets from multiple regions with RPO 0. Which one? Should I pick provisioned or serverless or limitless?
So this is a great use case for DSQL because it's regional, so you're trying to maintain consistency across regions. So that would be DSQL.
Yeah, and as of today, DSQL is the only service within the Amazon that does active with 0 RPO and RTO. Strongly consistent, so meaning both the regions can write at the same time, and at the commit time we decide who wins. And that's a perfect use case for DSQL. Obviously, if it's a NoSQL engine, you have DynamoDB, which does something similar, but it's transactional workload, so why? It's Aurora DSQL, of course. And again, these are hypothetical use cases for Aurora created. And this is just a brief summary of the strengths of each product. And the serverless and global database, these are just add-ons and features which is bolted on provisioned. You could change your provision to serverless. You could convert your hybrid cluster into a global database. It's just an add-on, like I said. And lastly, you have Limitless and DSQL. The DSQL is still in preview, so you may get to see a lot more features in the future. So please keep an eye on the documentation. And with that comes to an end. Thank you very much for your patience. Really appreciate it.